Okay, so here's our second example for related rates. We're doing it in the live session here, and we're gonna look at a pancake. So the Guinness record for largest pancake was set using approximately 150 cubic feet of batter. How fast was the thickness of the pancake changing when the radius was 10 feet and growing at 1 foot per minute? So there's our problem, and this is actually something that happened. Um, this pancake was actually made. I don't know if it's still the record for largest pancake. It was at the time when I came up with this problem. There's even a little note about it on the first page down here. All right. Um, so this is why I'm not sure if it's still the record, because this pancake was created in Manchester in 1994. So I don't know if anyone has attempted a larger pancake since then. It's kind of a niche record, so I'm not sure if someone has gone for it again yet. But yeah, at its final size, the pancake had a diameter of 49.25 feet, a thickness of 1 inch, and it weighed over 6,000 pounds, which is nuts. And they had to have like all this special equipment, a huge type of griddle thing made, and a massive flipper thing. So yeah, it was quite a feat. I should look up and see if that record has been beaten by now, since it has been a while. But this was the record holder at the time. So yeah, let's kind of look at our general procedure here before we jump into it. First things first, we're going to sketch a pancake. That's our scenario. We're going to label our pancake, and we're going to identify what we want to find. We're going to name our variables, see if anything is constant, and yeah. So let's start out with drawing a pancake. Okay. So we're going to simplify the idea here of what a pancake is going to look like. We're going to assume that it is roughly cylindrical, kind of a big, flat cylinder shape. Technically, I guess the sides might curve out a little bit, like these parts are probably not exactly straight, but for math's sake, we'll say that's a pancake. Gorgeous, isn't it? Put a big pat of butter on there and some syrup. All right. Now we want to label our pancake and think about what's changing and what's not changing. Well, we know the thickness of the pancake is going to be changing because that's actually what they're asking us for. So we should label that with a variable. So that thickness, I'll just call it H because that's usually what we call it when we're looking at a cylinder shape. You could call it, you probably don't want to call it T for thickness because T is already time in this problem. So we'll call it H. And then it looks like the radius is also changing because there's a mention of the radius growing at 1 foot per minute. So let's label our radius here. Okay, we'll call that R. And let's see, are there any quantities here that are constant? There is actually, spoiler, there is actually one, but does anyone know which quantity is a constant in this problem? Not R and not H, but there's one thing that doesn't change as far as this pancake is involved. Give the folks on the chat a second here. Time, well, time is gonna, well, time is our variable that is progressing whether we want it to or not. We unfortunately can't hold time constant at the moment. So time is changing. And then, yeah, there you go. The amount of batter. Nice job. So the amount of batter is not changing. They made 150 cubic feet, and that was it. As this pancake is growing and spreading, they're not making more batter and adding that to it. And they're not taking batter out of the pancake or anything. So the amount of batter is not changing. And that amount, you'll notice 150 feet cubed. Mathematically, what type of measurement is that? You can kind of check with the units there. Because yeah, I'll label this as a constant because that is great. Constant. Just plop out this big amount of batter and let the pancake spread. So any guesses on like mathematically what variable this might be or what type of quantity? Something in feet cubed? Eh? Doesn't look like it at the moment. So from the cube feet, or feet cubed, we can tell that this is going to be a volume. So this is a volume of batter that's not changing. So, so volume is really hard to draw in a sketch. So I'm just going to kind of put an arrow to the pancake. We'll say constant volume of V equals 150 feet cubed. Okay, but yeah, great job identifying that amount of batter. So yeah, that's a constant volume there. So we've got our sketch, we've got it labeled, we got a constant on there, we got our variables on there, and now let's identify what we want to find. So we can see what they're asking us for right here. How fast was the thickness of the pancake changing? So according to our variables on here, which variable is that referring to? Let's see. A base radius of 10 feet. Yeah. So we do want that for our particular instant in time. Yeah. A base radius of 10 feet growing at 1 foot per minute. So we want thickness change. So thickness change at the instant in time when the base radius is 10 feet. Okay, but that thickness changing, that would be a rate of change of h. And we know here in 3.8, our rates of change are instantaneous. So this is going to be dh dt that we want to find. So we want that rate of change when r is 10 feet. And we're also given this other little bit of information that the radius is growing or changing at 1 foot per minute. So that is a rate of change as well, instantaneous rate of change of the radius. So that's dr dt that's growing at 1 foot per minute. And we're keeping it positive there, positive 1 foot per minute because it's growing. Okay. So we've got a nice setup here for what we want to find. We know what we're looking for, dh dt, and we know when we want it. So what do we want? Thickness change. When do we want it? Right now. Or when the radius is 10 feet and growing at 1 foot per minute. So there we go. All right. So we now need to move on to the next step, which is to find a equation to relate the things that we're interested in and relate the variables and quantities that we have in this problem. And that really is based off of our sketch here. We've got a cylindrical shape, volume of 150 cubic feet. We would look at the volume formula for a cylinder, which is pi r squared h. So that is for a cylinder. That's why there's that page of geometry formulas, just in case you need to refresh. Okay, but in our case here, we could actually put that the volume is 150 cubic feet there. So 150 equals pi r squared h. Okay, since that is constant after all. Now we would want to take the derivative of this formula so that we can get some rates of change involved. So take derivative. Okay, and do it with respect to time t, because we are making rates of change here. So d dt of 150 equals d dt of pi r squared h. Okay, left-hand side here, the derivative of any constant with respect to any variable is just going to be 0. And then the right-hand side here, we actually did already. We did that in the warm-ups. So let's go snag that result. There. Hey, that looks kind of familiar. So there's a method to the madness here. All right, so in our case, with the problem we're looking at, since volume was constant, this rate of change was 0. There's no change in the volume for us. So we have a 0 there, but we can still take this whole right-hand side and use that. That way we don't have to do our product rule over again right now. But if you did need to do it from scratch, there was how we did it. Okay, so we're going to have pi r dh dt 2h dr dt. Okay. There it is. So this part did this in the warm-up. Okay, so we can put our pi r, and then we had r dh dt plus 2h dr dt. Okay, so we want to see what we have there. We're going to get our thickness change, dh dt. All right. So let's go ahead and solve this equation for dh dt. Let's see. Notice how this is factored already. So we could set pi r to 0, but the only way to solve that is if r equals 0, and that's not what we want. So we could say r dh dt plus 2h dr dt equals 0. Okay. And then solving for dh dt would mean subtracting 2h dr dt and then dividing by r. Okay. And we have quantities for a couple of those things. Okay, we have a quantity here for the radius r. R is going to be 10 feet. We have a quantity here for dr dt. Dr dt is going to be 1 foot per minute. And the only thing we don't have a quantity for right now is h. But it turns out that we can find one very quickly, okay, by using our equation again. Okay, because 150 equals pi r squared h, and so we can use that fact. Pi r squared h, and we know what we want our r value to be. So 150 is pi times 10 squared times h. And so that'd be 100 pi times h there. And so if you solve for h, you'd get 150 over 100 pi. Or if you reduce that down a little bit, that'd be 3 over 2 pi. So 3 over 2 pi feet for our thickness h. Okay, so sometimes you do have to do a little bit of calculation to find a value, but you should be able to come up with values, I mean, reasonably, in a reasonable amount of time based on what you have in the problem. So now that we have all the values for this right-hand side here, we can go ahead and plug them in. dH dt is going to equal -2 times h, which is 3 over 2 pi feet, times dr dt, which is 1 foot per minute, divided by r, which is 10 feet. Okay, and now let's simplify things a little bit here. We can do a little bit of canceling with some 2's there. All right, we can cancel some units with the feet. All right, and the rest you can plug into the calculator. You'd come out with -3 over 10 pi feet per minute if you do it by hand. Or if you do this on the calculator, that would be about -0.1 feet per minute. Okay, so that's what we come up with for the rate of change of the thickness of this pancake. So we'd put for our final answer, dH dt equals approximately -0.1 feet per minute. And then we would make sure that that is some kind of reasonable here. Okay, so the units here, we'll check that. Units are in feet per minute. Well, we'd be measuring our thickness in feet. Since we're measuring radius and everything else in feet, that seems reasonable for thickness over time in minutes. So the units are looking good there. Units. And then we check our value. The fact that it's negative makes some sense because as this pancake spreads out, it's going to be getting thinner. So this is going to be spreading out, the radius is increasing, and the thickness is going to be decreasing as it flattens. So thinning out. So that makes some sense. And the size of the value also seems in the right ballpark-ish. About 0.1 feet per minute. That'd be about like a little over an inch per minute or so. So that seems scale-wise relative to the very large radius of 10 feet, thinning out at about 1 inch-ish per minute seems reasonable. So value's okay, the negative's okay, the units are okay. So we've got our answer there. All right.